All right, let me hand the floor over to the BiAxis Solar Group.
Thank you. Welcome, everyone. Whereas Dr. Trom said, we're group 473P, who make up Kevin Diaz, Ethan Hines, Joseph Miller, Brendan Maurice, Charles Stone, Dan Viskosov, Devin Yan, and we're here to present to you our design we made. So our design focuses on simplicity with two motors that individually control the axis of motion. We have exposed gears on the outside of the device to allow for easy maintenance and problem recognition. And you can see the transition from our CAD model to the left and to our final built design on the right side of the screen. So our design focuses on simplicity, modularity, and strength. Simple being, like we said, the exposed gears and easy to view mechanisms. Modular, meaning our gears can be changed out for different gear sizes if necessary to create more or less accuracy, and generally a powerful design.
So here we can see some of our key product specifications that we were looking for in our design. Primarily, we focused heavily on a low cost per area. For us, that goal was less than $100 per square meter. And the other big goal that we had was to have a small non-reflecting area, which we'll see momentarily when we take a look at the design. Some of the other goals that we kept in mind throughout the design process were that our parts cost should be less than the off-the-shelf parts cost. Our minimum factor of safety, we aim for to be greater than 2. It should be able to work in the Las Vegas environment, which means heat mostly. It should have a washable reflecting surface. And then that kind of goes hand in hand with an operational lifetime, which we want it to be greater than 20 years. So some of the pictures here show the stages of our design from the first parts being printed to some of the practical tests of its capabilities. The wind tunnel testing subjected the heliostat to wind forces in several configurations to ensure that it would be able to withstand the environment of the proposed location without failure. These configurations included the safe mode, which had the mirror parallel to the ground to present a low surface area to the wind. And then we also had the angle which presented the most surface area to the wind as sort of a worst case scenario to endure the greatest amount of force. The testing apparatus also rotated the heliostat to ensure that all possible angles were tested. The final test performed was a targeting test using a stationary laser to hit specified locations at different angular positions to try and mimic the tracking of the sun to reflect to the collection tower. The size of the innermost circle that we see in the target, given the distance from a wall, reflected an accuracy of half a degree, which was the threshold set for the project goals. So the heliostat can be split into several subsystems based on function. The mirror's plate angle is controlled by the gear rings attached to the motors at a 5:1 gear ratio, which improves its accuracy given the limitations of the stepper motors chosen. The control box contains the electronics that the heliostat uses, and it also serves to offset the weight of the left motor, which otherwise may introduce unwanted stresses. And then just for a sense of scale, the height of the heliostat is 13.2 inches or 33.5 centimeters.
So here we have our main structure. Our main design consideration when developing this part was the wind survivability test, since this is going to experience the most stress when the apparatus is in the worst condition mode. So to do that, we tried to make it as stiff and short as possible to reduce this stress. So this is one of the two parts on the heliostat that was actually not 3D printed and was made from aluminum. So we decided to go with a square tubing to reduce the weight and to increase rigidity to survive that wind survivability test. And obviously the shorter height will also increase the strength of it. Then here we have our drivetrain assembly. You can see our two sets of gears that control the rotation in the two different axes. To design our gears, we needed to figure the proper gear ratio. So to do that, we used the 0.5 degrees of accuracy as our design consideration. So using the 1.8 degrees per step of the NEMA 17 stepper motors, we figured that the minimum gear ratio that we would need to achieve the 0.5 degrees was about a 3.6. But this is a theoretical gear ratio. So in real life, there is going to be some slipping between the gears. So to account for this, we put a cushion with our gear ratio on the design and increased it to 5, just for a good factor of safety. And then also another consideration when designing our gear ratio is going to be the torque inputted from the motor and it being able to actually move the overall assembly. So the maximum torque that the assembly was going to see was going to be from the weight of one of the motors itself. Since this motor right here is going to be moving as the elevation motor changes that angle. So to do that is just a quick, simple torque calculation from the weight. Just find the offset from the center of gravity of the motor to where the torque is being applied. And then that input torque from the NEMA is going to be multiplied by that gear ratio. So the input torque from the NEMA was, which value? It was going to, yeah, it's the 15.85 kilograms centimeters. And then the torque from the other motor is about 1.5 kilogram centimeters. So the input to out.
You froze.
And then just to sum up our drivetrain assembly, to reduce some friction in the rotation, we decided to use bearings in the rotation joints just to reduce as much friction as possible. And then we also incorporated limit switchings to allow for accurate homing for the controls. And then also to just drive in that modularity factor of our overall design. We went with standardized fasteners using 1/4-20s for the whole heliostat. There are only 3 different lengths of 1/4-20s.
So this part here is the control box on the bottom of the pillar. It contains all the electronics that our heliostat uses besides the 12-volt power supply. It has the breadboard with all the motor controllers, the microcontroller board, and the temperature and humidity sensor. It was added later in development once we had everything we needed, which is why we left. The pillar is a bit longer, and that's to accommodate the size of this box. The hole in the back feeds into the hollow aluminum pillar, and wires are able to be fed down through the inside of the heliostat to come out into this control box to minimize exposure to the air or the environment. And the hole in the bottom of the control box allows for the USB connection to our microcontroller board, as well as the 12-volt power supplies. Something we wanted to consider with this box design was to protect it from the environment. And that's something we saw in the tests where the humidity outside the box was about 45%, whereas inside the box, it was less than 20. Although the temperature was a bit higher, which is something we could consider in the future based on material considerations and the electronics that we use in the final design that we implemented, but it wasn't an issue with the practical tests we conducted. The motor control was done with C++ code in the Arduino environment. We used a SparkFun Thing Plus ESP32 board and NEMA 17 stepper motors. And the previous slide showed we used the SHTC3 temperature and humidity sensor. As mentioned previously, we used the
gear reduction to ensure we met the accuracy requirement of the project. The current setup requires that USB connection to a computer to send commands, but a final design would use Bluetooth or some similar wireless command sending to make that easier and more convenient. We also currently use a breadboard to connect all the wires, which is obviously not ideal because it presents a lot of failure points in the design. And so a final design would probably use some kind of printed board, and better tolerances would increase the reliability of that 0.5 degree accuracy requirement.
All right, moving forward, I want to talk a little bit about the dynamics of the actual heliostat design as it is going to hit targets. So our two NEMA stepper motors can move a maximum of 68 degrees in the elevation direction and 161 degrees left to right or east to west in our azimuth direction. This is due to a couple of physical obstacles present in the actual design. However, based off of the actual code that we made in order to actually hit the targets, it's still able to hit every target as desired. So on startup, using the limit switches, it's able to home to 0 degrees straight up for the elevation angle, and then it's able to home to -90 degrees in our azimuth motor. Our Arduino code basically uses a simple like spherical coordinates type of way, where our elevation is angle phi and our azimuth is an angle theta that allows us to sweep from left to right and then use the elevation in order to hit specific targets. Our code is actually able to take directly steps or allow it to move a certain amount of degrees. It's also able to get a specific target and then calculate the angles required for each of the motors in order to hit the targets, or do the opposite. When given a certain amount of angles, return the point in reference to its origin that it's going to be hitting.
Let's talk manufacturing considerations. So manufacturing ease was a big consideration in our heliostat design, with an emphasis on the ability to simply assemble, diagnose, and service the module after purchase. For example, the fasteners are selected based on low cost and common availability, with only 3 different lengths, and they can all be found at any hardware store. Other considerations are in using simple sleeve bearings instead of ball bearings for pivot points, and mechanical limit switches that serve for homing the mirror surface instead of more expensive solutions, all in an effort to bring costs down below $100 per square meter of reflective surface. Additionally, during rapid prototyping, we used 3D printed plastic instead of a different aluminum tube for every different design during our prototyping process to cut back on cost.
So here's the cost breakdown for our heliostat. Just going through the breakdown on the right, all groups were given a certain OTS components that were not considered in that 110 price ceiling, but it was still included just to give you a more complete cost breakdown. That included the DC power supply, the 2 NEMA 17 stepper motors and drivers, electronics and sensors, quick release coupling, and the mirror. So in addition to those costs, the ones that were actually accounted for include 3D printed parts, in which our design uses 0.387 kilograms of ABS plastic. Additional OTS parts, which for our design was the limit switch and all the fasteners used. And then in addition to that, we also included the cost and manufacturing costs and energy consumption correlating to those manufacturing costs of those custom-made parts that you guys saw earlier with the base. Our design also takes 7 minutes to assemble by hand. So that also includes the assembly labor with that cost. This comes out to a total cost for 1 unit of $48.99, $155.24 if you include those given OTS parts. And then we also included the cost of 3,000 units, which comes out to $146,970 or $465,720. Now, out of all the designs you'll see, why choose BiAxis Solar? So BiAxis Solar's main hedgehog concept was simplicity. We have a straightforward design that rotates across 2 axes, which allows for easy aiming of the mirror and just overall troubleshooting. And kind of playing into that same concept, our design is also very efficient. With a 5:1 gear ratio, our design allows for accurate and quick positioning of the mirror using those two NEMA 17 stepper motors. Additionally, our design is also very easy to control. It works on both angles and coordinate inputs, making it easily programmable if any adjustments are needed when implemented. Our design is only $48.99 a unit, $155.24 more realistically. So BiAxis Solar is both low cost and also quickly manufacturable and assembled in only 7 minutes. Finally, BiAxis Solar is also extremely modular, as all components are easily accessible for maintenance and have low manufacturing times with the standardizing of those fasteners across our design.
Thank you for listening to our presentation, and we're open for questions.
All right, thanks, guys. Questions from our panel?
If no one asks question, I'm gonna ask some.
Go ahead.
Okay. So I'm the cat talking here. One thing I want to comment on first is that you guys don't have the page number, so it's really hard when I want to comment on specific page. So let's go back to from the very beginning. So I think it's really nice you talk about at the very beginning that you use the exposed gear system for the simplicity, and I definitely agree on that. But have you considered about the durability if you actually use this exposed gear system actually outside compared to like if other groups do not adopt this like exposed gear system?
So we have thought about that, but I would say overall, it's more favorable for our design to be able to see the parts and see if there's an issue versus some of the more complex designs that have lots of have all of the working mechanisms inside. It also allows for easy maintenance themselves versus having to tear it all apart. So I think, of course, yes, it would wear more quickly compared to other groups, but our gears are also, I would also say, larger compared to other designs, so they're less likely to break apart.
Yeah, and that's also some of the other designs we looked at the beginning of this project used, some of them use linear actuators, which could be a bit more of a problem, especially if sand or other particulates are an issue, that would be a lot more susceptible, and there's not as easy a way to hide those from the elements as gears would be.
Oh, okay, great, thank you. And my next question is the wind testing. I don't know which. Yeah. So this one. So you did the wind testing without the mirror installed on the thing, right? Because I see that. So does it really reflect? I don't know the consideration why you do not consider put the mirror there when you do the wind testing, because there's actually a big cut out there. It may have different results if you have mirrors installed and without mirror installed, right? I'm not quite sure.
So I would say it would have some effect. The effect that it would have, it would increase the weight of the top of the mirror plate slightly. And that would be the only thing that would cause it. However, unlike other groups, our design was actually experienced a higher wind test than other groups, just by happenstance. For one, we're only supposed to be able to pass the very high wind test in the safe position, which for us is the mirror plate directly parallel with the ground. However, because of the time of the mirror plate, we were using not all of the parts that would later be on it. So we were using 3D printed model motors, not the actual motors. And during the test, the motor part disengaged, and our heliostat fell into the unsafe mode, which thus essentially produced it showed that our thing was even able to withstand the strongest of the wind in the unsafe position, which is perpendicular to the ground.
Oh, okay, okay, great. Thank
I
you.
would, I would also like to add on top of that, that our main structure at this time hadn't been manufactured out of the aluminum square tubing yet. So this is actually a 3D printed main shaft as
Okay.
well.
Okay, okay. And I also want to ask about the shaft. You talked about, I think on one side you said you decide to use the square shape. And my question is that why square shape do you think you think is better? What kind of failure mode you consider, and why square is better than like circular tube?
Part of the reason is how we attach the motors.
Okay.
So the number of holes that would need to be drilled into the side or machined. It would be a lot easier for manufacturing to create those holes and get a stable connection for the one motor attached to the main structure.
Okay. Okay. So it's not for like structural consideration, but it's for easily assembly and the motor. Okay. Okay.
We also did consider, like through the wind testing, we knew it would be exposed to kind of high winds. So we didn't want it to ever kind of rotate in that position, even though it would be fastened. It would just easier, like to the base, it was already in a square shape.
Okay.
To just kind of attach everything.
Okay. And there was one slide. I don't know if it's my internet problem or it's the presenter's internet problem. I think it's frozen for like 1 minute. It is like torque hold, torque in, torque out. Could you please explain that a little bit? Yeah.
Yeah, I don't think he realized it, but he was cut out towards the end there when he was presenting it. All that he was saying at the end was the calculations showed that the torque provided by the motor was more than enough to
Okay.
rotate the required parts.
Okay, so torque in is required, torque out is the torque generated.
Yes, correct. Yeah.
What is the torque hold?
So that's the specified holding torque of the NEMA 17 motor from the material spec sheet. And then the torque out is that torque multiplied by the gear ratio.
Oh, okay, 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 great. And at the very end, when you talk about cost, is this the cost of like, we can consider there should be a difference if we produce like a 1 unit and a 100 units. So this is based on producing 1 unit or like 100 or 1,000.
Yeah, because this was just the cost of one heliostat, and that's kind of all we tested. But like if it was implemented, we were told they would be using 3,000 units. So we just included that cost as kind of general.
So this is based on producing 1 unit, but if you plan to produce like 3,000 units, the cost will be a little different, I guess.
Yeah, it all depends on what the whatever company is implementing this heliostat design, what they're able to get, because obviously a lot of these prices are what we paid or what the department paid for, and the company will be able to get these a lot cheaper in some places, like getting parts in bulk or more efficient machining shops to do the work. So the prices are all subject to change, but almost certainly they'd be far lower than what we calculated, not high.
Okay, thank you. So overall great job, and I think you guys answered the question very well. So congratulations. I'm done with my question.
Thank you.
You're welcome.
All right. We've got time maybe for one more question if Rick or Elise, if you guys want to jump in?
Hi, yeah, this is Elise from Cummins. I was just wondering, how does the mirror mount to the support?
Currently, the mirror we were given has its adhesive on the back, and so we affixed it that way. In a final design, that's not really the best for longevity, and so there'd be a more permanent fastener we'd probably implement to attach the mirror in that way.
Our mirror plate has holes for additional 1/4-20 bolts. In our final CAD, like Joseph just mentioned, we didn't have that since we were just using the adhesive part, but we would plan to use 4 1/4-20 bolts to secure the mirror.
Okay, thanks. And one more thing, for the gears, what material was it? Were those just 3D printed?
Yeah, they were 3D printed.
Yeah, in general, just all the red components that you see on the design, those are 3D printed.
Okay. Yeah, I was just wondering if you did any dimensional variation analysis, looking at how alignment of the gears and any issues would have with assembly. And also looking at like the contact stresses and also any, if there's hit by a rock or something, and if they would break as well, like have any forces in the thin direction.
There were a few instances where it was actually while we were testing the controls code where the motor hit the rotation hit a physical limit, and the full torque of the motor spinning was just putting stresses on the gear, and it never.
Okay.
We did reprint a few times, so it's possible that if that happened multiple times, it could eventually fail. But our code eventually put in fail safes, so it should never put stresses directly on the gear like that in actual operation.
Okay, great. Thanks.
Okay, very good. Well, just to kind of stick with the schedule, let's wrap it up there. We're meant to have a 5-minute break, but the 5-minute break ends at 11:40, so we'll have maybe a 2-minute break. I did just drop into chat the Zoom link for the next group. So Dr. Dong, Elise, Rick, if you're available and want to pop into the next one, that's where we'll be at 11:40, which is 2 minutes from now. But yeah, I want to thank you guys for the presentation, for all your hard work this semester. I think aesthetically, this is a super cool design. Like we were debating with the superlatives, giving out the design for most steampunk, and you guys would have won had we done that. But the teaching team, thought maybe that wasn't appropriate, so we ended up not doing that. But at least in my mind, you guys are the steampunk winner for the semester for this very cool looking design. Great. So that brings us to the end. So let me stop recording.